Hi everyone, thanks for taking the time to attend this talk. I'm Marta, I'm a developer advocate at Ververica, and today I want to talk a little bit about change data capture and some of the tools that make it easier to put it into practice effectively. So for those of you who have never heard about Ververica, you might know it as the company of the folks who created Apache Flink. And this means that I'm really fortunate to work every day with the core Flink maintainers and to be involved in this really thriving and active open source community. And what Ververica does besides working on Flink is provide an enterprise Flink distribution called Ververica Platform that simplifies a lot of the operational side of deploying and maintaining streaming applications in production. And since the beginning of last year, we are part of the Alibaba group, which you may or may not know is also one of the biggest users and contributors to open source Flink out there. So before turning to Flink, I was working as a data warehouse engineer for a couple of years. And this is a pretty good depiction of me at work. So if you were ever involved in building data integration pipelines for analytics, in a company that is not necessarily running on the latest cutting edge tech, you probably know that there's nothing very sexy about being a data warehouse engineer. There is a lot of legacy, a lot of technical debt, you have a lot of late data or just this we'll fix it later data. And you really have no option but with time just learn to live with it, which is not very good. So this is all I knew for a long time. So you would have this monolithic application that was backed by some transactional databases. You would write these huge heavyweight ETL jobs to integrate the data, enrich it, and so on to make some sense out of it. And you would give your stakeholders something that serves a specific business purpose. So in this universe, databases are still very much seen as these static sources of data records, like just a collection of state about your business that is sitting there waiting to be queried. And for a long time, I was also guilty of thinking about databases like that. But in reality, most of the data that is stored in these databases is continuously produced and is constantly evolving and changing. And it's the logic that you use to query this data that doesn't change very frequently. And when you start looking at things from this perspective, you seriously start questioning a lot of things. Like, if our data is being continuously produced, then why are we giving stakeholders data from yesterday? Why are we not offloading the load on the database throughout the day so that people don't have to wake up in the middle of the night because some query ran out of memory? And in general, why are we just letting all this data go stale before we process it? And let's be honest, no one working with data integration wakes up thinking, well, I really can't wait to scan a production database for changes using a 100 light query with 1,000 business logic conditions. That will probably fail at some point. So what I described so far is actually also change data capture. So this is not a new concept in itself. The idea behind it is pretty simple and is not that recent. So what you want to do with change data capture is you want to track and propagate data changes in a database to downstream consumers. And so whenever you get insert, an update, or a delete operation in your database, you want to capture this change in state and make it available to, in our case, our analytics workloads. So when change data capture is done right, it can be a huge enabler for different use cases, not only in the analytics space, but also for things like caching validation or syncing between microservices and so on. And if you want to learn more about change data capture and the use cases and patterns that it enables, I really recommend that you follow Gunnar Morling and explore his collection of talks. He's the main Debezium guy, and he has really, really good insights about this topic. So there are basically two different ways that it can go about change data capture. The first one is what I talked about so far and what I was using on a daily basis at work before, which is called query-based change data capture. And what happens here is you periodically poll your database for changes, and each time you just ask, did anything change since the last time I checked? And this has some advantages for some use cases, and is a bit simpler if you, for instance, just want to track a slowly changing dimension or something like that. But for most use cases where what you want to do is react to data as soon as possible after it's generated, it kind of carries a lot of problems. So the first problem is that some data changes might get lost in between the polling of the database. So if you're running this query every 5 minutes and in this interval a record changes state twice, you can't really capture that. And in the same way, if a record is deleted, you just really lose track of it. There is no way for you to know that the record is no longer there. And there's always a trade-off between how frequently you can query your database and also the load that you're incurring on it. And this is especially true if you're sharing resources with other teams. So there must be a way to do this differently, right? And what if we just tapped into the transaction log? So all databases have an immutable log that just registers all the transactions that are successfully executed in the system. So in Postgres, this is called the write-ahead log. In MySQL, it's the bean log. And this is what a database administrator would use for disaster recovery to kind of roll back the state of the database to before everything went to shambles. This is the base of Logbased CDC. So what you do with Logbased CDC is you use this transaction log, you just tail it, and you get the latest changes, and you propagate those downstream in near real time. So this guarantees that all data changes are captured because you're reading from the log, and it just registers all operations, including deletes. And you get more context on the actual changes, so you can get the state of a record before it changed. After it changed, you can get the operation that was performed on this record and other very useful metadata to kind of reason about your data. And also because you are no longer reading from the database, you are reading from this transaction log. So this has very minimal impact on your source databases. So your DBA will probably love you for this. And the most popular tool to do this log-based CDC these days is Debezium. And what's great about it is that it gives you a standard format for this change event. So you can process the data in the same way regardless of where it's coming from. And what it does in essence is really transform your databases into event streams that can be consumed in near real time. So Debezium is built on top of Kafka and provides Kafka Connect connectors for the most common databases, so MySQL, Postgres, MongoDB, and so on. And once the change events are pushed to Kafka, you can basically consume them with pretty much anything, including Flink. If it's your first time hearing about Flink, in the simplest form, what it does is it continuously consumes data from this disparate amount of sources, like the change streams from Kafka that I was just talking about. It applies some stateful computations on these data streams and builds up some context about the data that it's processing as it goes. And then it just produces some kind of output. So it can be an API call, updates to a database, other data streams, and so on. So what makes Flink really powerful and different than other stream processors out there is that the way it handles this context, or the way it does state management, which gives you some really, really good properties like enabling you to process streams with low latency and also high correctness guarantees. And what makes Flink really flexible is that it does one at a time event processing, or what some people still call these days real streaming. And this gives you a really great primer to address a wide range of use cases, from streaming analytics and machine learning to these Lambda-style event-driven applications. And as a user, Flink gives you different APIs to choose from that trade off how easy they are to use and how expressive you can get. So at the higher level, you have APIs like SQL, the Table API, and Apache Flink that are a bit closer to this relational way of thinking about data. And these APIs allow you to express your problems in a very concise way and kind of offload all the operational heavy lifting to Flink. So you don't really have to think about state management or any of that. And as you progress down, using the APIs gets a bit more complex, but you get more and more control over the programs that you're building and how they are executed. And when you reach the core building blocks of Flink, there is really no limit to what you can do. And for some use cases, you need Flink's full work horsepower. You need to perform really complex computations, and maybe you need to customize a lot of your programs. But for a lot of others, you don't. And CDC is a great example of a use case that can benefit from how simple it is to use Flink SQL. So the nice thing about providing a SQL-based API to the streaming is that everyone knows SQL, right? If you've used a database before, you recognize this as standard or ANSI SQL. And this means that you also know how to use Flink SQL from the get-go. And you'll notice the resemblance in a bit when I start the demo. So what's different about running SQL on top of a streaming engine? So unlike what happens in your regular database where you run your query and the engine takes a snapshot of the table at the time the query was run, and then it just computes the results based on that static snapshot. What happens in a streaming SQL engine is that your query is continuous and never ending. So you first deploy your query, and then whenever there are some changes to your tables, these changes are just continuously consumed, and the results are continuously updated. So, like I said, this is long-running, the queries are long-running, and it only really finishes when you actually stop the job. In a nutshell, what Flink SQL gives you is this high-level, relational-like way to query data streams using this language that you already know. So it's optimized to handle batch and streaming workloads in a unified way. So this means that you can use the exact same query to process real-time data and, say, a file stored in a S3 bucket. And besides all the operations that you're already familiar with, like joins, aggregations, filters, it also has support for advanced operations like time traveling, pattern matching, and things like this. And with something as simple as SQL, it really allows you to build applications that leverage all the benefits regarding performance, scalability, and consistency of any other Flink program written in Java or Scala. And you have a whole ecosystem around it that makes it really easy to write end-to-end streaming applications using just SQL. So now we can get down to what actually brought us here in the first place, which is Flink SQL and change data capture. So since Flink 1.11, which was released last month, Flink supports to consume JSON-encoded Debezium changelog from Kafka. So the way to do it is simply to use Debezium JSON, the Debezium JSON format in the properties of your Kafka back tables, and then Flink is able to just deserialize the format. And now to a quick demo about how you can easily just set up a CDC pipeline using Flink and Debezium. What are we doing with this demo? So for the sake of this demo, we're looking into some fake insurance claim data related to animal attacks in Australia. And what we'll try to do is basically get a change data capture pipeline going, simplify some things by using Flink's integration with catalogs, and then maintain a materialized view in Elasticsearch that is updated in real time with whatever transactions are happening in Postgres. The demo is using a Docker Compose setup that you can clone from GitHub. I dropped the link down there. And the setup spins up a couple of containers that run different services. So we have Postgres that is bootstrapped with some demo data, which will be our source of change events. We have Kafka and Kafka Connect to deploy Debezium to get these change events. And we have a Flink cluster and a SQL client that will allow us to submit some queries to Flink. And finally, we are syncing the whole thing to Elasticsearch and Kibana. To spare you some time looking at my terminal, I started all my services before. So the first thing we can do is check that everything is up and running. So we just use docker compose Paes, and we can see that all the services that I mentioned before are up and running, so we can get cracking. So the first thing we can do is check that we have some data on Postgres. So we can start our Postgres client here, and we can just check what tables are in there after the client is up. Okay, cool. So now we can just check in the information schema what tables we have in this database. So we have 2 tables, members and accident claims. And now we can just do something like count how many records we already have from the bootstrap that we did. So we have 1,000 records in this table. That's cool. And what we need to do next is deploy our Debezium connector. So for that, we will post a JSON document with the configuration of the connector to the Kafka Connect running service. And this should give us back the properties of the connector. Cool, so you can see here that we are using the Postgres, the Debezium Postgres connector. We want to track our database, which is named Postgres. We are using PG claims as like the prefix for any Kafka topics that are created from this. Yeah, then there's some properties that are set. I will explain it a bit better in the README of the repo, just to make things a bit easier, like decimal handling mode and that kind of stuff. So what Debezium does, unless you tell it not to, the first time it connects to a Postgres server, is that it takes a consistent snapshot of all the schemas. So what should have happened now that we deploy the connector is that we already see events in our Kafka topic. So we can just use the Kafka console consumer to have a look in there. This might take a little while. My computer is literally on fire from Docker. But so we saw that we had a count of 1,000 events. So that's 1,000 records in our Postgres table. So this is kind of what we should see here. Here we go. So you see that it's just reading the topic that we created from our Postgres table using Debezium. And you can see here that we have kind of like the tail of our topic. So what happens is that you see in the payload, you see the before, because this just comes from the inserts that we did when we spin up the container. There was no before state, it's an insert. And then you get the whole description of this record. So this is good. And what we can do next is actually do some changes on Postgres, and then we should be able to see these operations being captured in Kafka. So let's do first an insert of a new record, and we will follow that with an update of that same record. So just update to get like a receipt in there. And then we can immediately also delete the record. So what we should see when we go back to Kafka, we should see three events. We should see insert, we should see update, and we should see the delete. So let's have a look. We have here the insert. You can see here that we created a new record, and then it was followed by an update, and this is the state before we made the change, and then you also get the state after, which should have like the new receipt that we added. And then also you can see here the delete. And we can move over now to see how we can make this, how we can now propagate this to Flink. So we can start the Flink SQL client. When you see a squirrel, it's a good sign. Okay, so now we have our Flink SQL client. This is basically a tool that you can use to submit queries or jobs to Flink. What we want to start with is create a catalog that will give us access to the metadata of the external tables that are stored in Postgres. So we run that, so JDBC catalog. Cool, and we can use the catalog to check that we have the same tables that are available on. The thing we want to do is create a table to consume the change events from. So it should have the same schema and constraints as the source table. And like I said, with the catalog available, we can just easily do this. So you see, we're using the Kafka connector. We are tapping into our PG claims, accident claims topic, and we are using the Debezium JSON format. Also, we are scanning from the earliest offset so that we can get what's already, so we can consume the topic from the beginning. So we do that. And since we're already here, we can also create a JDBC source table for the existing members table. So like this. And after we created all our tables, we can just change to the default catalog. You can see that the tables that we created are here. And now we can select from our changelog table. So here we go. We should hit 1001, which is all the records that we have in our topic. Oh, actually just 1000 because we deleted the record. So what we can do now is just do the same that we did to test how the integration was going in Kafka. So now we can just insert a new record, and you see that it is immediately propagated to Flink. And same thing if we do an update on this record, you can see that the claim total received has changed. Now we can also just scratch it, and the record should be deleted from the Flink table. Cool. So now imagine that we want to calculate and visualize the aggregated insurance costs per insurance company. And we want to bucket this by the accident detail, or what animals are causing the most harm in terms of costs. So we can create a table that will sync to Elasticsearch like this. And by specifying a primary key, we are telling the Elasticsearch sync table that we expect it to work in absurd mode so that we can update our aggregated values whenever there's an event that changes in them. And also we are using an index that I haven't previously created on Elasticsearch, but Flink will take care of creating this for you. So we can just create this table, And now we will just insert with a query that basically creates a concatenated or creates a key that is concatenated from the insurance company first for characters, and then also part of the accident detail field. And then we are aggregating, or we are summing the total of claims per insurance company and accident detail for every claim that doesn't have a status that is denied. So if we run that, it's submitting a job to the cluster. So now we can switch over to Kibana and create a simple dashboard that then we can use to see the changes in real time. I will skip over this part and come back when we have a dashboard. But you can see that we already have here the aggregated insurance costs index that we created by creating a sync table with Flink. You can see now that we have created a dashboard in Kibana that is basically showing the aggregated costs per insurance company, and then also the aggregated costs per accident detail, which is basically the animal that caused the accident. And now what we want to do is we have a small data gen script, and we will run that, and hopefully what we can see is this dashboard updating in real time. So we start this, we move back to Kibana, and we should see that our values are changing. So basically what the datagen script is doing is just inserting every half second new records. And you can see when Kibana updates and refreshes, you can see the values just change. That's about it for our demo. So I would like just to wrap this up by telling you that Flink SQL is used at massive scale in companies like Alibaba, Uber, Yelp, and Lyft. As an example, if you take Singles Day in 2019, which is probably the biggest shopping festival in the world, Alibaba was running, I think, around 10,000 Flink SQL applications on over 5,000 nodes, and dealing with a data size of around 985 petabytes. And at peak, they had a throughput of 2.5 billion events per second, and they were still able to process that with sub-second latency. And their biggest job was handling 100 terabytes of state. So this should give you a good idea of how far you can push Flink. And yeah, Flink SQL is standard. So if you know SQL, you will know how to use Flink SQL. It provides unified APIs that allow you to work the same way with batch and streaming data, and it has a really growing ecosystem of integrations around it. So I would just like to add that in the upcoming releases regarding CDC in particular, you can follow what's planned in this umbrella ticket, but the most relevant features that are coming up is support for Avro. So this will be much better to work with actually the schema information that Debezium can also provide you. You will be able to do temporal joins with changelog sources, and at some point, batch support will also come to CDC. I recommend that you check this open source Flink CDC connectors that were developed by one of the main engineers that is working on CDC in Flink. And these are using embedded Debezium, so you don't really need to deploy Kafka Connect and Debezium itself, so you can check it out and give it a try. And lastly, I would just like to really thank DataEng Bytes, especially Peter, who's been like a really great supporter of Flink and of bringing Flink down under. So thank you so much, and it was a pleasure to do this talk for you.